All right, this video is going to be about the adjacency matrix and how we can use it in graph theory. It is another way to describe a pairwise relationship or an edge between vertices on a graph. So here I've got a sample graph, and we do have a multiple edge and a loop contained in this graph. And what the adjacency matrix does, much like the matrices that we saw in the previous unit, describes a from a certain vertex on the row to another vertex that's labeled in the column. So for instance, here vertex A is going to go from A, and there's an edge connecting it to B. So we have two edges actually, that connect vertex A to B. There is no vertex connecting A directly to A, like for instance a loop. So we see the element 0 from A to A. Then from A to C, there is one edge. And from A to D, there are no edges. So we can just keep filling in.
Let's pause to try this for yourself.
And this is what we see. Notice the symmetry along the main diagonal. Let me see if I can highlight that here. Here's the main diagonal of the matrix, because it is a square 4x4 matrix. So we see the elements reflected across that main diagonal. All right, and we're also going to look at digraphs, which we have talked about and used some digraphs, but we haven't technically defined. They're just graphs with directional edges. So you'll see arrows that tell you the direction of that edge. And if we don't see an arrow, then we assume that the direction of the edge goes both ways. So let's fill this one in. Here, from A to B, there's only one edge. There are no edges from A to A. I guess I should have started there. No edges. But from A to B, there is one edge. And then from A to any other vertex, there are no edges. From B to A, there is one edge, and this is that one edge. Here, you see the arrow. That's from B to A. B doesn't have a loop, so we'll put a 0 here from B to B. There's no edge directing us to C. There's no edge directing us to D either, even though it looks like, and in the last graph we had that edge, but notice the direction. We can't go from B to D. So I've just filled in the rest of the elements in this matrix. Now notice this one does not have symmetry, and that's fairly normal for a digraph, since these edges do have a direction or arrow. Now the interesting thing about using a matrix for graphs are that we can do math with matrices pretty quickly anyway in our calculator. So if the power of an adjacency matrix represents the length of a path from one vertex to another, then the elements in the matrix represent the number of paths that same length. So for instance, right now the power here of this matrix is understood to be 1. So a length of one edge is the way we created that adjacency matrix for this digraph. Now I'm going to use my calculator, and I've already put the same matrix here, this same matrix into the calculator. You can see I've got it labeled as matrix A. So if I square this matrix, let me bring this one over here. This matrix now tells us how many paths there are of length 2 from any two vertices. And length 2 because of the power 2 here. So for instance, there is one path from A to A of length 2, and it would go like this. That has a length of 2. There are two paths from D to A. So let's see, length of 2, 1, 2, could be like that. Or this one. So those are the two paths.